We have a smooth steel ball, a piece of shelf standard, which will serve as a ramp, a quarter here, domino here to stop the ball. If we release the ball, it will roll down the ramp, and it will clearly roll faster and faster, so that if we want to graph the ball's velocity versus time, the ball starts with 0 velocity, and let's assume that we start our clock at the instant of release. Then the origin is going to correspond to the fact that the velocity is 0 when the clock time is 0. And the velocity is going to increase. So does the velocity increase along a straight line? Does it perhaps increase at an increasing rate along a curved line? Does it possibly increase at a decreasing rate? So we don't know which of these is the case. Although if we look into the physics, we're going to predict that if this ramp is indeed straight, then the velocity should increase linearly with time. If we increase the slope of the ramp, of course, we expect the velocity to increase more quickly, and if we assume that we have a straight line velocity versus time graph, then we expect the graph to be steeper. If we have a steeper ramp. And I'm going to say a steeper graph for a steeper ramp, not on a steeper ramp, because the graph isn't on the ramp. In any case, this should be fairly clear. Now, if this is the case, if our slope is constant, then that means that our derivative of v, which can be written as v prime of t or dv dt, is constant. If we let this constant be a, and that's going to stand for acceleration, because this is actually the definition of acceleration. If we let v prime equal a, which we assume to be constant, then integrating both sides of the equation with respect to t, our left-hand side is going to yield integral v of t plus an integration constant. Our right-hand side is going to give us the function a times t plus a constant, and we'll let this constant absorb the constant from this side, and we have a velocity function which is equal to the acceleration multiplied by the clock time plus some constant. You might wonder about the influence of that constant. Well, if I give this thing a push at the beginning, we still expect the ball to speed up. And we actually, because of the physics, expect it to speed up at the same rate. The ramp will have the same slope, but it no longer has a 0 initial velocity. So if we were to graph our velocity versus clock time for the situation we just saw, our velocity would start at some non-zero value and increase along the same slope as it would if we started from rest. That is, our value of a would be the same, but our constant c would be different. And we would be able to identify our constant c with the velocity at t equals 0, because if t equals 0 on this side, we get c. If v equals 0 on this side, well, if t equals 0 on this side, well, we get v of 0 then equals c. So whatever our initial velocity was when we released the ball would be the value of c. We'll see more about this as we proceed in the course, but this is a fairly typical type of application.